Each tower stands on a massive watertight chamber called a caisson. The caisson rests on a bed of gravel, 3 meters thick. Below the gravel, nearly 200 steel piles are driven deep into the seabed. But the tower supports aren't physically connected to the piles. A large collision would cause them to slide on the gravel and transfer the energy from the hit via friction. It's known as an isolated system.
So it's just standing on friction, but you know, you have a huge normal force coming down, so friction is extremely large.
And that means if the Dali had crashed into these towers, the result would have been very different.
So the collision in Baltimore wouldn't have caused the bridge in Turkey to collapse. Had the towers and all the weight from the main cable and the girder and the traffic and everything, that in principle goes vertically down through the towers into the seabed.
But building this kind of defense system is a colossal task. The massive concrete caissons are the size of city buildings. They're built on land before the dry dock is flooded. The giant structures are then floated out and slowly towed into position. Each caisson is rigged up with a remote-controlled ballast system. It guides their descent, accurate to 10 millimeters, as they sink 42 meters to the sea floor, settling onto the specially prepared gravel bed, ready to receive the record-breaking tower system. Boston is one of the windiest cities in the United States, and wind proved to be the Achilles heel of the massive glass panes.
It had a large amount of glazing, and during the construction process, some of the windows began to actually fall out, and these windows weighed 230 kilograms, and they fell onto the pavement load. What they did, they replaced them with plywood as like an interim measure. So the locals jokingly referred to it as the Plywood Palace, which I thought is quite a nice term.
Streets were blocked off on gusty days to protect the public.
And it took a while to find out the issue was really with the glazing itself, and there was some internal cracking, and that led them to actually fall out or to be damaged.
The windows were replaced, but the building had another disastrous wind problem.
So people said they felt motion sickness towards the top of the building.
The problem was vortex shedding. Vortex shedding can be seen from space. As wind passes by mountains or tall islands, creating dramatic cloud swirls in their wake.
Those are vortices, okay?
Behind tall buildings, especially those with sharp corners, the vortices can set up a dangerous pressure differential.
So the wind's coming at me, and it first goes to this side and that side, and then as it creates those vortices, it's a low pressure, so I get sucked a little bit to the side. And then the next vortice is on the other side, and I get sucked to the other side.
This oscillating flow can amplify a building's natural resonance, causing it to sway. The next generation of nuclear reactors are designed to prevent serious consequences, even if a meltdown happens.
If you do get into a station blackout scenario, so you lose on-site power, you lose any way of controlling your reactor, you absolutely have no way of mitigating externally the situation. The fuel doesn't melt down in whatever time it normally would.
Flamanville 3 is the first generation 3+ plant in France. Designed to be the safest nuclear plant ever to be built in the country, which has a long history of atomic power. The most sensitive buildings are housed in a double containment structure, built to withstand severe impacts, like a plane collision or earthquake. The reactor itself is on a 6-meter thick concrete mat and surrounded by a steel vessel which is protected in a concrete pit. But in a worst-case scenario, it's nature that comes to the rescue.
The key shift is between Generation 3 and 3+ is the introduction of this idea of passive safety features.
In the rare event of a core meltdown, a core catcher, a giant water pool below the reactor, can catch and cool molten radioactive material when it drops. This is what is known as passive safety, using a natural force like gravity to provide protection in a worst-case scenario.